So first of all, how many of you already know what binary search is? Like how it functions, how it works and stuff like that. You can just raise your hands. Okay, cool. So most of you don't know how it works. Okay. So binary search. So now the let's say you have an array of 6 numbers. Right. And now you need to find the let's say you need to find the location of 5 in the array. Right? It is over here. So it's at the 0, first, second, third, fourth. It's at the fourth index. Right. Now, if you want to find which index it's located at, you can simply uh, loop through the entire array. Wait until you find the element. Whenever you find the element, then you can just return the index. Right. But that would be an O of n algorithm. Right. That's essentially what a linear search is. Right. We are linearly moving through the array, and then whenever we find the element, we are just returning. But what we can use a simple observation that the array is sorted, right? So if the array is sorted, then we can easily, let's say, so the whole concept of binary search is pretty simple. We so if we look at the middle, we'll divide the array into two parts, right? Then we look at the middle element. So now let's just both of these are middle elements. Let's just say that 3 is the middle element. We're looking for 5. If 5 appears in the left half, then we'll search in the left half. If 5 were appearing in the right half, then we would search in the right half. That's pretty much all binary searches, right? We simply need to figure out where the number is in relation to the middle element. If it's on the right, then we'll search on the right. If it's on the left, then we'll search on the left, right? So, let me just show it's working. This is a nice and easy case where we can see how it works, right? So let's say we are binary searching for 33, right? It's right here, right? So now this element is 33 over here. Now the middle element would be 53. Now 33 is towards the left of the middle element, right? That means all of the elements which are over here are going to be larger than 33. If these elements are larger than 33, then obviously we won't find 33 here, right? So we'll get rid of this whole part. Then we'll look at the middle element. We'll check where 33 is, where 33 is in reference to the middle element, right? So 33 is larger than 25, so it cannot be in this part, and we'll get rid of that part, right? Same thing. We'll find the middle element, check where it's so it's at the left part, so we'll get rid of the right part. Then eventually we'll find the middle element, right? And this is the middle element. We have found it. So essentially we are at each point of time we are. So for example, let's say the array is of length n, then we'll find the middle element and then we'll eliminate one half of the array. So let's say we are eliminating the right half, then the size of the array would become n by 2, right? And similarly, the size would be n by 4, n by 8 until it becomes 1, right? So now let's say this takes k steps, then like just simple math, the first, second, third, fourth would would be, since we are uh, this would be n by k power 0. This is n by k power 1. Eventually we'd have This 2 to the power 0. N by 2 to the power 0. 2 to the power 1. This is n by 2 to the power 3. Right? Eventually, we'll have the last element, which is the answer. This would be n by 2 to the power k. Right? Which means 2 to the power k is n, and k would be equal to log 2n. Now, k is the number of steps we'll take to find the element. So this searching algorithm works in log of n time, right? And this is the basic concept of binary search. It's just whenever it has just one condition, the array must be either non-decreasing. So if it's like 3, 4, 4, 5, 6, something like that. So now notice that this is a non-decreasing array, or it is a non-increasing array. That means it's 4, 4, 3, 2, 1, something like this. So this is a non-increasing array. So whenever you find a non-decreasing array or a non-increasing array, then you can apply binary search to it. Right? Are there any doubts up to this point? Everything's fine. Now let's. So this is the basic concept of binary search. Now let's actually look at some code. Right. So so whenever we are so this code is written in C++. I hope most of you are comfortable with C++. So in this we have two elements, L and R. This is the lower bound. This is the upper bound. Right? Uh, then we are looking. This is the middle element. We'll check, and we are looking for X. We are finding X. So we'll this would be L. This would be R, and somewhere over here we would have mid. Right? So we'll check if the element is equal to the middle element, right? That is, we'll check if this element is equal to X. If it's equal to X, then awesome, that's our answer. And we'll say answer is equal to mid and break. But if it's not equal to X, if AR mid, which is this element, let's say that this is less than X. And let's just assume that this array is an increasing array, right? So if this array is increasing, if AR mid is less than X, so that means X would be at some point here. If this happens, then we can eliminate this part and only look at this part, right? So we'll update L with m plus 1, right? On the other hand, if X were on this side, then we could have eliminated this half, and then in that case, R would be equal to mid minus 1, right? So notice that in each case, we are just changing the boundary of the search condition, right? So initially it's L to R, then let's say it's in this side, so it becomes mid, which is mid plus 1 to R. Then let's say it becomes this and this and this. You can see that the search space is getting smaller and smaller, right? So this algorithm would run in log 2n time. Okay. Now this is the code for binary search, but there are a lot of binary search is very, very infamous, right? Because it's really hard to implement. So let's look at this case. This is similar to the previous case. Only in this case, let's say we are looking for the first element which is greater than or equal to uh, X, right? So in 1, 3, 5, 7, 9, 11. So and let's say X is equal to 10. right? So we're looking for the first element which is greater than or equal to 10, which is over here, 11, right? So in this case, mid would be equal to L plus R minus 1 by 2, right? So L is 1, R is 1, 2, 3, 4, 5, 6, 6. So mid becomes uh, 6, 3, right? 1, 2, 3, 5. If AR mid, which is 5, if this is greater than or equal to X, which is it is not, so we'll write L equals to mid plus 1. So L becomes equal to 4, R remains 6, mid becomes 5. Then we'll check if the element at the fifth position, which is 1, 2, 3, 4, 5, 9. We'll check if 9 is greater than or equal to 10, which again it's not. So L will be equal to mid plus 1, 6. R would be equal to 6. We would now notice that since both of these are equal, we'll no longer go into the while loop. Since R must be greater than L, whatever, then we'll return L. This is our answer, L. But there are a lot of implementing this is pretty difficult. So notice I'm doing this. I'm sure a lot of people are confused with this thing right here. Okay, so in C++, L plus, so if we do L plus R by 2, this will give us the floor value of L plus R by 2, right? So, and we need to assign mid to L plus R by 2. So why am I doing this weird sort of way of doing this? That's pretty simple. So with negative numbers, floor works a little differently. So can anyone tell me what minus 5 by 2 will give? So if we do minus 5 by 2 in C++, then what will we get?
-2, or is it -3?
Which one should be the answer? Right. So let's say this is minus 5, minus 4, minus 3, minus 2, minus 1. So and minus 0. So we need to find L plus R by 2. So let's say R was minus 5. No, L was minus 5 and R was 0. So what do you think should be the correct answer? If we look at positive numbers and look at negative numbers, what do you think is the correct answer? Minus 2 or minus 3?
-3.
So minus 3, right? So because here we have 6 numbers, here we also have 6 numbers. Here, if this is the first number and this is the 1, 2, 3, 4, 5, sixth number, then we'd simply do 1 plus 6 by 2, which is 3.5. The if we floor it, and then we'll get 3. 1, 2, 3. So this is the first, second, third number, right? So we want first, second, third number, that is minus 3. Unfortunately, see, whenever you do minus 5 by 2, C++ will give you minus 2, right? Which is not correct. Which is, I mean, not correct would be an understatement. This will give you a infinite loop, right? Which is obviously not something that we want. So instead of doing L plus R by 2, we can do L plus R minus L by 2. Notice that R is always greater than L. So R minus L would always be greater than equal to 0, right? Or rather, would always be greater than 0. If R minus L is always greater than 0, then this would work fine. And this plus this would always be equal to this, right? Because this is, you can write it as 2R plus L minus 1, which is equal to L plus R by 2. Right? These both are the same functions, but we can write this function as this little complicated version of this, simply because with negative numbers, uh, the rounding down part does not work as normal. This is a very, very good tool to remember because a lot of errors occur with ceiling and floors for negative numbers. -5/2 will give you -2, and ceiling might give you -3, which is the opposite of what you need. Right? So instead of this, we simply always work with positive numbers. So that is one little caveat sort of thing. And let's look at the same thing. So now we were looking at the first number which is greater than equal to x. Right? Now let's look at this part. And over here we are checking with the first we are checking if it's greater than equal to x. Right? Let's check if it's less than equal to x. Right? Now this is the same problem. We are checking if it's less than or equal to x, right? So instead of greater than equal to x. Everything else is exactly the same. So let's just look at some case. So again, let's look at we need to find the six where six is. Initially L is equal to 1, R is equal to 6, mid becomes equal to, let's ignore this +1 part for now. Right? Let's say we are doing it like we normally do. So again, uh, L plus R/2 would be 3. We look at 3. Now we'll check if 3 is less than or equal to x, which it is, which it actually is. So L becomes equal to 3, R becomes equal to 6. Right? Again, mid would become equal to 3 plus 6/2, which is 4. We'll check if 4 is less than or equal to 6, which it is. So L would be equal to 4. And then again, mid would be equal to 5. We'll check if 5 is less than or equal to 6. 5 is less than or is less than 6. So L would be equal to 5. Right? L is equal to 5, R is equal to 6. Mid is, we'll divide this by 2, mid is 5. We'll check if 5 is less than or equal to 6. It is. So we'll set L to mid, but mid is still equal to 5. Right? So you notice the infinite loop, right? So we go 1, 6. We go 1, 6, 1, 6, 3, 6, 4, 6, 5, 6, but we stay at 5, 6. And this creates an infinite loop. Even though we're doing this exact same thing, right? Uh, the only difference between this statement and this statement is that there's the less than equal to sign here, and over here there was a greater than equal to sign. Everything else is exactly the same. The whole concept is exactly the same. We're checking for the, we are dividing it into halves, then we are checking the left part, then we are checking the right part. The only difference between both of these statements are in one we are checking the left part first, and in this we are checking the right part first. But this is a incorrect implementation, well this is a correct implementation, right? So this this will give you an infinite loop, right? So this is an incorrect implementation. Therefore, you always need to check. We always need to check for the R would be. So we always need to check for the left half first. If we are checking for the right half first, then we are getting an error, right? But there's thankfully an easy way to get rid of this error. We can just add a plus one. So now this this is not equal to the floor. This is equal to the C, right? So if it's 5 plus 2, this by the way is uh, sort of trick. 5/2 floor is 2. 5/2 seal is 3, right? In C++, 5/2 is 2 and 5/2. So to get the seal value, we can add 1 here. So this would be 6/3. This is 3, right? So if we need to find the ceiling of A by B, this we can do like this. This is a pretty useful trick. So instead of, or otherwise, the only other way to find the ceiling of 5/2 would be to convert it into a floating point number, and then convert this into an integer number, right? So instead of writing integer of C of this number, we can simply write a plus b minus 1 by b, right? So if it's L plus r by 2, then this would become L plus r plus b minus 1 by 2, right? So this would be L plus r plus 1 by 2, right? So we use the seal, right? So in this case, we are adding 1, and this 1 makes this whole expression equal to L plus r by 2, L plus r plus 1 by 2. Right, now how would this work? Now how is this different from the previous case? Well, pretty simple. Um so let's look. So if we look at the same case again, we have 1 and 6. L is equal to 1, r is equal to 6. Mid would be this L 6 plus 1 plus 1 by 2, right? This is 7 plus 1 by 2. So mid is 4 now, right? Before mid was 3, now mid is equal to 4. Everything else is exactly the same, but over here mid becomes equal to 4. Then again, 6 plus 4 plus 1 by 2. This would be 10, 11, which is 5. Mid becomes equal to 5. 5 to 6. Now, previously, we were doing 5 plus 6 by 2, which gave us 5, and it would run into an infinite loop. Now we are doing 5 plus 6 plus 1 by 2, which gives the 6, right? So now L would be 6, R would be 6, and this would fail the condition R greater than L, and you would exit, right? So now this means that we would exit out of this loop, and we would avoid the infinite loop. Avoid the infinite loop, right? So this is very important. So these are two implementations. You just need to check if you're going for the left half first, or if you're going for the right half first. If you're going for the left half, we need the floor. Otherwise, we need the seal. Right now, obviously, this is only applicable for the case where it's greater than, where it's increasing. Uh, if the array is decreasing, then everything would function pretty much the same way. The only difference would be a difference in signs. But make sure that you remember this, and while you're implementing binary search on your own, you'll notice that often it goes into an infinite loop. In that case, just try adding a 1 here and see what happens. In most cases, when you add a 1 here, it would take the ceiling value, and you'll get the correct answer. Right, so just dry run the cases and check if giving it a 1 gives us the correct answer, or if we need a 0. So that's the basic difference between both of these binary searches. And yeah, so these are some basic implementation of binary searches. These two implementations are much more important than this implementation, right? These implementations work even if we don't exactly know if it will ever be equal. See, because in this case, let's say if x does not appear, if x does not appear, then this will not give us any answer, right? Because we are only giving an answer when we find the element. If we don't find an element, then answer would still be equal to -1. Since answer is still equal to -1, this is not that useful, right? Personally, I've done a lot of CP, and I've never really used this implementation. You always use one of these implementations. Both of these implementations are equivalent. You can feel free to use any of them. Just make sure that you don't fall into any errors. Now, right now, we are only thinking about binary searches, right? We don't have to limit ourselves to a binary search. We can use the binary search concept 1 second. Get a new slide. We can use the binary search concept with any increasing function. Right now, let's look. An array of 5 elements can be thought of as 1, 2, 3, 4, 5. Right now, think of it as a function. Let's say a function index which would return AR index. Right. So now this instead of AR mid, we write function mid instead of AR mid, and everything else would remain the same. Right. The only difference is instead of AR mid, we write function. And so now we can use, so this gives us a better understanding of binary search. Right? Binary search does not need to work only with an array, it can work with a function. So binary search can work with any increasing or decreasing function. I should write non-increasing, non-decreasing, right? Because even if we find duplicate elements, binary search continues to work. Right? So binary search does not need a function, an array. It can work with a function. So any increasing or decreasing functions, right? So for example, f of x equals to x squared plus 5, right? Now this is an increasing function. For f of 1, we'll have 6. Uh, for f of 2, we'll have 9, and so on and so forth. You can see that this always increases. So we can use binary search in the same way to calculate, to let's say find x, find smallest x for which f of x is greater than or equal to 15, right? So we can use binary search in the exact same way to find the smallest number for which f of x is greater than or equal to something, right? So we don't really need an array. We can also use a uh, function. Okay, so that is one part, and binary search, it's not really that complicated. I think the most of the parts have already been covered. One final part is how do we work binary search on real numbers. Now, have you guys ever worked with real numbers in C++? Right, so float, double, numbers like this. Have you ever worked with these numbers?
Yes.
Okay, so these are pretty infamous, right? Because these work, these don't work good, right? So for example, if you have 2.55555 and something, and let's say you have another number which is also 2.5, but your compiler might suddenly uh, say that both of these numbers are not equal, because C++ works like that, right? Representing floating point numbers are not easy, and you'll find a lot of errors like these. Right? So whenever you find so instead of so floating point numbers, we never need to find an exact value. We always need to find an approximate value. Right? So it does not matter if we are getting 5 or 5.00001, as long as it's less than some epsilon. This epsilon might be 10 power 8, 10 power minus 7, or something like that. This is essentially how much error we can handle. Right? So binary search with real numbers would work almost the exact same way. This is binary search with real numbers. So cout precision, I'm not sure if you guys know about this, but this essentially tells us how many digits do we want to calculate the precise value of, right? So let's say if we do 18, then we'll the all the functions, everything will be calculated for the first 18 digits, right? So if you are getting an error when you're working with code forces or something problems, make sure that your precision is pretty high, right? But apart from that, binary search works the exact same way. So this is an example of finding the square root of a number, right? If you need to find the square root of some number, then how do we do it? So square root would be x square, right? This is an increasing function, right? As x increases, f also increases. Since it's an increasing function, we can use binary search on this. That's pretty much the only thing that you need to check, right? You just need to check if it's an increasing function or if it's a decreasing function. If it's any of these, then we can use binary search. But if the some function is parabolic or if it has more local minimas, then we can't use it. We can only use it if it's increasing or decreasing. Right? Okay. So now, how do you find the square root of a number? Uh, Look at let's do a dry run. We'll probably so right now I'm taking. Notice that I'm taking L is equal to 0, R is 1e9. 1e9 is essentially 10 power 9. So I'm so if I have some number x, I need to find what its square root is. It does not the number can be as large as 10 power 18, whose square root can be 10 power 9. Right? That's why I've taken the bounds as uh, L is equal to 0 and R is equal to 10 power 9. Epsilon I've taken as 10 power minus 9. Generally, this would be given by the problem, as in how much error it's fine to handle. So actually, binary search with real numbers is counterintuitively easier since we don't really have to worry about bounds. Right? Notice before we had to worry if it's from L to R or if it's from mid to R or mid plus 1 to R. Right now, we don't have to worry about any of that. Right? We'll simply do mid is equal to L plus R by 2. Right? You can always think about this function as L plus R by 2. Um, it works the exact same way. The only difference is negative numbers would give a different answer here and a different answer here, and we need this answer, right? But it's fine to always think of it as this, right? So we'll find the middle number. So middle number of these two would be some 1e9 by 2, right? Now then we'll put this number mid in our function, which is mid square, right? This would give us 1e18 by 4. This is obviously much greater than mid, right? So R would be equal to mid 1e9 by 2, right? Exact same thing as normal binary search. So uh, initially it looks like this, then it will go like this, there. Eventually we'll go. Let's say we have already figured out the bounds to 0 and 30. Or 0 now. Square root of 28 would be 5 point something something something, right? Now let's say we already know it's between 5 and 6. Then we'll find whatever is the middle of these, which is 3. Then again, it's not here, it's not here. Eventually, we'll go between 5 and 6. Now normal binary search, 5 and 6, fine, cool. Then we'll go to mid plus 1, 6 and 6. That would give you an answer. That would give you an answer of 6, whose square is 36. This is the first integer whose value is greater than 28. But we don't want this. We need the exact or at least exact value up to this epsilon, right? So now let's say L was equal to 5 and R is equal to 6. Mid now becomes equal to 5.5, right? In normal binary search, we won't have even gone to this point, right? But now we'll check with 5.5, right? So we'll find what 5.5 squared is. We'll check if this value is less than or equal to 26, 28. If this value is less than 28, then we'll search from 5 to 5.5, right? Then mid will be equal to 5.25. Then we'll check if it's greater than or equal to 28. If it is, then we'll search from 5.25 to 5.5, right? We'll keep lowering the the search space until the difference between L and R becomes very, very small. How small? Epsilon small, right? So we're checking while the search space, which is essentially R minus L, while this search space is greater than equal to epsilon, which is our error metric, while this is true, we'll keep searching. The moment we the difference between these two is less than epsilon, at that point we'll stop our search. And that's the only difference between binary search between integers and floating point numbers. But one a little interesting thing with this, let's say your L is equal to 0, R is equal to 10 power 9, and epsilon would be equal to 10 power 9. Can someone tell me what the time complexity of this would be? You know, it's log of something, right? Can you tell me what this something is in the case of real numbers, right? Not integers, real numbers. Can someone tell me what the time complexity would be in this case? Anyone? Okay. So the time complexity in the normal case would be log of search space, right? Which is 10 power 9. Now, the difference now is that the search space has increased. See, because normally the search space would be from 10 power 9, 0 to 10 power 9. But right now, between 0 and 1, there are a lot of numbers, right? 1.01, 1.02, 1.03, 1.04. We're not taking that into consideration. So, how many numbers are there between 0 and 1? In this case, let's just assume that there are 10.9 numbers between 0 and 1. Why? Because epsilon is equal to 10.9. Right? So if they are between 0 and 1, if there are 10.9 numbers, so between 1 to 0 to 10.9, there must be 10.18 numbers. So the time complexity would not be equal to 10.9, it would be log of 10.18. Right? So you can see the time complexity increases when we are doing binary search with real numbers. Uh, up, you can see that obviously it doesn't increase because we are dealing with logs. This can be written as 10.9 square, which is just 2 times 10.9, right? So time complexity is increasing, but it's increasing linearly, right? So we can still use binary search on real numbers and it would work completely fine, right? Now, that is it with binary search. Are there any doubts about binary search? If there are not, then we'll look at one question. Are there any doubts? The whole part, real numbers, others numbers, any doubts?
Could you explain the last part once again, the time complexity part?
Okay, so for real numbers, for integers, uh, if let's say L is equal to 0 and R is 10 power 9, then how many numbers are there between these two numbers? Right, they're 10 power 9. Now, not like they're 10 power 9 plus 1, right? But approximately they're 10 power 9 numbers, right? That is because between L is equal to 0 and R is equal to 1, there's just one number, or rather two numbers, right? 0 and 1. But in the case of real numbers, between L is equal to 0 and R is equal to 1, there are a lot of numbers, right? 0.001, 0.002, 0.003, so on and so forth, right? Now, since we have taken epsilon as 10 power minus 9, epsilon is essentially, you can think of epsilon as the maximum precision or whatever you call it, the number we are going. So if it were 10 power minus 3, then we'd go up to this number, right? 10 power minus 1, 10 power minus 2, 10 power minus 3, right? So if between 0 and minus 1, you'd have 0 0.001, 0 0.002 up to 1, right? So there are 10 power 3 numbers at the epsilon b, 10 power minus 3. Since the epsilon is 10 power minus 9, there are 10 power 9 numbers between 0 and 1. So between 0 and 1e9, there are 10 power 18 numbers. Since we are looking in a search space of 10 power 18, now you can think of it as exactly the same as normal binary search. Now there are 10 power 18 integers, and what would be the time complexity be now? It would be log of 10 power 18, right? Instead of log of 10 power 9. Is that clear?
Yes.
Okay. Any other doubts? Okay. Now. So now let's look at a problem. Okay, actually, okay. So let me quickly cover ternary search before we look at the problem. This is ternary search. This is a slightly advanced topic. You'll probably not find a lot of problems on ternary search, but just for the sake of completeness, I'm covering this. So now ternary search, uh, unlike binary search, you can see we are dividing by 3 here. Why are we dividing by 3? All of these things are not important. Right now, you can think about ternary search as a type of search which applies to functions which are parabolic. Right? You can see that this function is parabolic. It increases, goes to a maximum value and decreases. Right? So if a function increases, then decreases, and there is only one local maximum or one local minimum, then we can apply ternary search. Right? So now in binary search, the condition was it should be either non-decreasing or non-increasing. Over here, the search should be monotonically increasing, then monotonically decreasing, right? Like this or like this. Another thing in which is different about ternary search and binary search then is that there should be only one local minima or maximum, right? So we cannot have equal numbers, right? So for example, uh, if our array was something like 1 2 3 4 3 2 1, if our array was something like this, then notice how the array is first increasing, it's reaching to 4, then it's decreasing again, right? You can see that this is the exact shape that we require for ternary search. Since this is the shape we require for ternary search and there's only one local maxima, we can apply ternary search. But had there been another 4 here, then ternary search would have failed, right? Because there is more than one local minimum. If it's not monotonically increasing, then monotonically decreasing, we cannot apply ternary search. Okay, that is the condition for ternary search. How does ternary search work? So, okay, let's take this example. Again, we are doing the same thing that we did before with L plus R minus 1 L by 3, again for negative numbers. So now let's try and apply ternary search in this, right? So now let's say we're searching for the number 3. Okay, so another thing in ternary search is it does not work like a normal searching algorithm. We cannot just search for any digit here. We can only search for the local maxima or the local minima, right? So now this is the case when it's increasing first, then decreasing, right? So we are looking for a case like this. this function would be applicable for only this case. So like this, and we need to find value of the local maximum or local maximum, global maximum. Both would be same in this case, but we are essentially looking for the value of the local maximum, right? So function. What is the function? Now, like I said before, you can think of this array as a function, where function of x would simply return arx, right? And since this array is increasing first, then decreasing, this is a correct function for Ternary search. Okay, now how does this work exactly? Now, Ternary search. So let's say this is the L value, this is the R value. Now, in binary search, we would have looked at the middle value. In ternary search, we look at values which are 1/3, which are at a distance of 1/3, right? So now let's say this whole arc has a distance of r minus L. So this distance would be r minus L by 3, right? This point would be L plus r minus L by 3. And the same thing over here, we'll find r minus L by 3, right? So now this distance would be r minus L by 3, this distance would be r minus L by 3, and this distance would be r minus L by 3, right? So essentially what we're doing is we are dividing the whole array to 3 parts, right? Before we were dividing into 2 parts. Now we are going to divide it into 3 parts, right? So one part, this is the first part, second part, third part, right? Then we'll check what's the value over here, right? So if we do a dry run, then L would be equal to 1, R would be equal to 6. So M1 would be R minus L by 3, which is R minus L by 3, 5 by 3, which is 1. So L plus 1 would be 2. M2 would be 6 minus 1, which would be 5, right? So we'll go look at the second number, then we'll go look at the fifth number. Now, since the fifth number is greater than the second number, then since this part is between this part, then we know that the answer is definitely not in this part, right? Because it's decreasing in this part. We know that, and since we are looking for this point, the answer must be in this part, right? So we are eliminating 1/3 of the array. Instead of eliminating half of the array, now we are eliminating a third of the array, right? Now we know that the answer is in this part. Now again, we're going to divide it into 3 parts. So then L, so now since we know that the answer is in this part, L would now become equal to 2. L is equal to 2, R is equal to 6. Again, we'll subtract 2 divided by 3. M1 would be 3. M2 would be equal to 5, right? Again, 3 and 5. Both of these are equal, so it doesn't really matter. And R would be equal to M1, right? Then L would be equal to 2, R would be equal to 5, and so on and so forth until we find the middle element. So like this, we're dividing it into 3 parts. Then we are looking for this part, right? So we can eliminate this part, right? So now let's say it's over here and here, then we can eliminate this part. And it's here and here, we can eliminate this part, and so on and so forth. We'll keep eliminating parts until we reach this point, right? Once we reach between these points, then we'll simply find which is the local minima. That's essentially how ternary search works. It's a little complicated. Honestly, I don't think that you'll need it. Um, if you'll need it, then you'll be able to just go and copy some implementation somewhere. Notice that there is an additional step over here because it will fail when the difference is less than 3. right? Because if the distance is less than 3, then this would return 0, and so there would be no updates. If there are no updates, it would be an infinite loop. So this is just an implementation caveat. Apart from that, this is essentially how ternary search works. Um, it is fine if you don't understand how exactly it works, because you can simply just copy this implementation, just change the value of function. All you essentially need to know is that the function should be either uniformly monotonically decreasing, reduce to a local minima, then increase, or it must be increasing, go to a local maximum, then decrease. So if the function is in this form or this form, then you can apply ternary search to find the local minima or the local maximum. That's essentially how ternary search works. Uh, I'm not going in depth in this, but just remember, if we find a function like this or like this, then we can apply ternary search. Now, binary search, one very important thing about binary search is, even if you understand how binary search works, it's difficult to do problems. So this site is Codeforces. I don't know if you guys are familiar with this site. You should be. But even if you're not, this is the site for Codeforces, and I've just selected a binary search problem, right? So now this is somewhat hard, but I think it's very important to do a problem like this, because binary search is always asked in this format, right? It's always asked in a problem like this. So quickly, guys, just take like 2-3 minutes and read the problem, and I'll explain it to you. If there are any doubts for the previous parts, feel free to ask. But if not, then please read the problem. Okay, so I hope you have read the problem. I'm just going to explain it really quickly. Uh, so in this problem, we are given two strings. We're given a string P and another string T, right? And we are also given a permutation. Permutation is just a numbers where the numbers don't repeat and the numbers are from 1 to n, right? So we're given a permutation of numbers, let's say 4, 3, 2, 1. And these numbers are these, and the character at these numbers are getting deleted one by one, right? So if we look at this example, so t was initially equal to NASTYA, right? Nastya. Then when the first element of the array A is equal to 4, right? So if the first element is equal to 4, in the first move, we'll make the following removal, right? So we'll go to the 1, 2, 3, 4, T, and then we'll remove T, right? So in the first move, we'll remove T. In the second move, we'll look at 1, look at the first element, remove the first element. Then we look at 5, find 5, 1, 2, 3, 4, 5, remove the fifth element, right? Remove the third element, second element, and remove the sixth element. So essentially, we have a string S, we have a string P. We are removing a character one by one in this order. So we're removing the fourth one first, then the third one, then the second one, then the first one. Right? We need to figure out. We need to figure out what is the maximum number of characters we can remove. We need to figure out the maximum number of characters we can remove such that the characters which have not been removed can form T, right? So for example, let's say the word was apple, right? And let's say in the first move remove P, and in the second move we remove A, right? So the array must have been 3, 1, right? And other elements, right? But we have P and E. Now we need to find if we can form another string which is T, if T can be formed by deleting some number, some characters of this, right? It basically means that T must be a subsequence of the string after deletion of the numbers, right? So now what is a subsequence? For example, let's say we have A, B, C, D, E, F, D, E, C, for example, would be a subsequence, right? Because we can delete this number and we'll get CDE, right? Now notice that because for being a subsequence, they do not need to be in order, right? B, D, E would also be a subsequence, right? So essentially, we need to check if the string P is a subsequence of the deleted string T, right? So I hope the question is clear. If there are any doubts about the question, you can ask it now. If not, then I'll detail the solution. Is the question clear? Okay. So the question now reduces to find maximum characters we can remove from T to get S, right? So S is the new string, which has all the characters of T after deleting some characters, such that S is a or rather such that P is a subsequence of T, right? This we can simplify the question like this. We need to figure out the maximum characters we can remove from T to get S such that P is a subsequence of this actually should be S, right? Now we are removing the numbers according to the array AR, right, which is a permutation. This would tell us how in which order we need to delete the elements, right? So we need to delete first element, second, third, fourth, fifth, right, in this order. And after deleting the element, so for example, S is equal to A, P, P, L, E, S, right? So if AR was equal to 6, 1, 2, 5, 3, 4, then after deleting after first move, so we are deleting the sixth element, A, P, P, L, E, S. So we're deleting the sixth element. String would be apple. We need to check if let's say P was something like LE, right? So if P is equal to LE, then we need to check if LE is a subsequence of S, right? Now notice that LE is in fact a subsequence of S, right? Since we can delete these three numbers, then we'll find LE. Since it is a subsequence of X, first move can be a valid answer, right? So I hope the question is clear. Now, why is this question? First of all, why is this question binary search? Uh, this is probably the most common way binary search is actually asked in programming competitions and your like CDC internships. It is not immediately obvious that this question can be solved using binary search. Right? You notice that the value of P and T are all quite large, right? So log of 200,000 would be a very, very small number, right? So it does not really tell us that this is a binary search problem. You can think that, oh, there must be some sort of linear solution, but no. In problems like these, there's an n log n solution, right? Now, what is this n log n solution? Now, notice that uh, in our question, let's say, let's say, um, let's say the actual answer was 4, right? So A, P, P, L, E, S, and L, E, and let's say this is 1, 2, 3, 6, 4, 5, right? So the answer in this case would be 4, right? We can delete the first, second, third, and sixth element, and then we'd still be able to form LE, right? But now notice that had for a value 2, right? For for num equal to 2, where num is the number of moves, we can still form LE, right? If we do 0 moves, then we can still form LE. If we do 1 move, we can still form LE. 2 move, we can still form LE, right? 2 moves, that means we are deleting the first element. Second element, what are we left with? We are left with PLES. PLES. Notice that LE is a subsequence of PLES, right? Since it's a subsequence of PLES, we can still form, the answer, this, then 2 is a possible answer, right? But we need to find the maximum answer, right? So essentially, what does the function look? So we are getting, so for 0 moves, we can form the subsequence. Same thing with 1, same thing with 2, same thing with 3, same thing with 4. But for the fifth move, that means we're deleting first, second, third, and then we're deleting the sixth element, and we're deleting the fourth element, right? So now in this case, S would be E, and P would be equal to LE. Now, obviously, LE is not a subsequence of E, right? There are more elements over here than here. So fifth move, we'll have no, right? So notice that the function, even though that it's not exactly binary search, the function is first increasing, then decreasing. So for 1, it is yes, 2, it is yes, 3, yes, 4, yes, 5, no, 6, no, 7, no, and all of these no before yes, right? So it is initially yes, then no, right? So now if we can write yeses as ones, then we can think of it like this, right? So notice that this function is decreasing, right? And notice that this function is continuously decreasing, right? So it is a non-increasing function, right? So this is a non-increasing function. Now, the moment we find that this is in fact a non-increasing function. Now we need to find the farthest move up to which the answer is true, right? So basically we need to find the first time the answer is false, right? So notice that a function, so notice that this becomes a binary search problem, right? Because we have found a non-increasing function. What is a non-increasing function? The non-increasing function is essentially after x moves, check if possible subsequence. So if after x moves, if it's a possible subsequence, then we return true, otherwise we return false, right? So we have a bunch of ones, then we have a bunch of zeros, and that's it. The moment we find that this is a function like this, we can apply binary search to this. So this is the code I wrote for binary search. I'm just going to quickly go through it. So we have, so these are the two strings that we have. This is our array, right? So this is just the input output part. This is our binary search part, right? Now in this, notice that binary search is not how we normally do binary search. There is an extra part, this. So what is this part? Now let me just go through the algorithm. So we find the lower bound and upper bound for the answer. Right now, notice that the answer can be a minimum value of 0. That means after 0 moves or 0 removals, and the maximum value can be n after n removals. Right? So we'll find the mid. Notice that we are doing ceiling over here. Why are we doing ceiling? I've already explained this. For binary search, we are checking the left half first, so we are doing ceiling first. Right? We'll find a string s. Then let's say we need to figure out if an index has been deleted or not, right? Now we'll go up to mid, right? So if we are going now over here, notice that mid is our answer essentially. Mid is essentially the answer or the number of moves. We'll go from 0 up to the number of moves, right? So if there are 5 moves, then we'll go up to the 5th index, right? Then in this array, now let's say we are checking for 3, right? So we'll notice that the first, second, and third elements, that is the 5th element, the 3rd element, and the 4th element, has been deleted, right? So we'll update is deleted array. So is deleted will essentially store if an index has been deleted or not, right? Then we'll iterate through the array. If an index has not been deleted, right? So if an index, if is deleted is still equal to 0, then we'll push that to our string s, right? So s is essentially a string which we get after deleting mid numbers, right? So after deleting mid characters in this order, the string that we get is s, right? Then we will check if s is a subsequence, if our string b is a subsequence of s, right? This is the code to check if a string is subsequence of another. This is a classic problem. Uh, if this is a very classic problem, not that hard of an implementation. I'm just going to quickly go through it. So let's say in this case, if the string, if a is greater, if the size of b is greater than a, then obviously the answer is false, right? Because a larger string cannot be a subsequence of a smaller string. Otherwise, then we'll simply iterate through the array, and whenever both of these elements become equal to each other, we'll increase some iterator it, right? And if it becomes equal to the entire array, the size of the array, then we'll return true, else we'll return false. Right? This is a very, very classic code. You can find this online. It's a very simple code, very easy, and it's a very common to us. If you don't understand this, you can quickly Google uh, how to check if a string is a subsequence of another. Right? But this is the code to check if a string is a subsequence of another. So if the string s, if the string b was a subsequence of s, then we'll update l equals to mid. Right? Otherwise, we'll put r equal to mid minus 1. Right? So this essentially means that we are going through the entire array. We are checking for a particular value of mid if it is a possible subsequence. If it is a possible subsequence, then we'll stop at this point. So for example, if the array would be something like 1 1 1 1 0 0 0 0, right? Just for simplicity, I'm just looking as the function as an array, right? So now in this case, L would be 1 2 3 4 5 6 7 8. So L is equal to 1, R is equal to 8, right? So we'll mid would be equal to 4. So we'll 1 2 3 4. So we'll check if mid is equal to 1 or not, right? So we'll essentially check if the function at 4 is true or false. If it is true, then that's all well and good. But we need to find the last element for which the function is true, right? Now, if it is true for this point, then that means the last element for which it is true must be over here. It cannot be over here, right? So now mid would be equal to, so we'll update L with the value of mid, right? So now L would be equal to 4, R would be equal to 8. Then again, mid would be equal to both of these divided by 2, 6, right? 4, 5, 6. This value would be false, right? Now, since this value is false, we are looking for the first value which is equal to 1, right? We are looking for the last value which is equal to 1. Since this is false, everything over here must be false. We are looking for 1. We're not looking for zeros, so we'll get rid of all of these values. And then L would be equal to 4, R would be equal to mid minus 1, 5, right? So over here, notice that 4 plus 5 by 2, we are not looking at this, we are looking at this, right? The ceiling value. So we are checking mid is equal to 5. Then for mid equal to 5, which is this value, again it's false. We since it's false, it's a 0. Everything over here must be 0. We are looking for a 1. We'll get rid of this value. Then L would be equal to 4, R would be equal to 4. We would exit and we'll end up with 4, which is essentially the last value for which function is 1, right? You can also think of it as the maximum value for which function is true, right? So now once we have so so binary search can be used in problems like this, right? So in the code, all of this is just a function, right? All of this part plus this part is just an increasing function. It's just a continuously non-increasing or a non-decreasing function. We are just using a function, then we are checking if this function is true or false. If it is true, then we are looking for, then we are getting rid of half of these values. If it's false, then we are getting rid of half of these values. Then we are looking for the smallest value. We are looking for the largest value for which function is true. That's essentially how you solve these problems, right? Now notice that the complexity in this case would be n log n, right? Because this with complexity is n, right? From 0 to n. Over here the complexity is n, right? So and since this while loop will run log n times, and each time it's going to run O of n times. So the time complexity of this solution would be O of n log n. Right? This is probably the most important way binary search is asked in most programming competitions and your CDC interns, whatever is going to happen now. This is the most common way binary search is asked. Right? Binary search is rarely asked in its normal form, just find an element in a sorted list, right? It is always uh, asked in a question like this, right? And to solve questions like these, you need to figure out what the function is and if the function is continuously increasing or decreasing. If you can reduce the question into a function which is continuously increasing or decreasing, then you can easily find the maximum or minimum value, right? This is how you solve this problem. You can see that this solution has been accepted. Are there any doubts about this question? Because this is very important. Is there anyone who did not understand?
So basically here we are just removing the element and checking if the string is the substring is present in the current string.
Yep,
Okay.
that is all we're doing. The only thing apart now, notice that had we only used that observation, then we would have needed to check for all of the answers, right? We would have to check when move is equal to 1, then when we are removing two numbers, when we are removing three numbers, then we are removing four, so until when we are removing n numbers. That would be in O of n square algorithm, right? But since we notice that if we remove seven elements, and let's say we cannot form a string after removing seven elements, obviously removing one more element will not help us in forming that string, right? So if our deleted string is already not a subsequence, deleting more numbers will not make it a subsequence, right? So the moment you notice that uh, the function is increasing or the function is decreasing, that moment you can start applying binary search to a problem, right? Are there any other doubts? Okay, so I think that is pretty much everything that there is when we are dealing with binary search. Notice that this problem, even it is rated 1700, right? It's a div to D problem. But the moment you understand that, yes, it's a binary search problem, it becomes fairly simple. The only thing that you need to figure out is to check whether it's a binary search problem or not. So yeah, I think that is all there is to binary search. Is if there's any doubt regarding binary search or just regarding anything, right? The session is pretty much over. You can leave if you want. If there are any doubts regarding anything, any problem that you're facing, CDCA or any code forces thing, feel free to ask. Otherwise, I'll end the session.
Okay, I think let's stop the recording for now. If any of you have any doubts, you can speak up.